Okay, hello. Thank you for the introduction. So today I'll be talking about my work on the effectiveness of modular testing with EvoSuite. So modular testing refers to testing a component of a program in isolation. And effective tests for a module can provide documentation, find bugs, and prevent regressions, which are sometimes preferred at the granularity of an individual method. So for C programs, automated testing of a particular method typically requires a harness or a driver. So this example shows a fuzz driver for htslib, which is a C library for handling genome sequencing data. So the driver takes the data parameters from a testing tool and sets up the program state before invoking the target method htsclose. So although the goal of modular testing is to test a unit in isolation, setup calls are often required for non-trivial execution. So for effective testing of a file close operation, this requires first opening the file, shown here. So in this work, we explore modular testing of object-oriented programs in Java, and we choose to study the regression test generator EvoSuite because its generated prefixes are a target for many recent works in modular specification generation. So in its default mode, EvoSuite generates tests at the class level and optimizes for branch coverage of the entire unit through an evolutionary search. EvoSuite also has a modular testing mode, which is activated by specifying a target method through a command line flag. So in modular testing mode, EvoSuite's evolutionary search algorithm is limited to create prefixes including only the specified method itself and constructors of the method's class type. And this strict limitation prevents the algorithm from selecting setup methods, resulting in low branch coverage. So if you consider this following example from the defects for J benchmark, this get legend items method. The method begins with a nullness check on the field plot. And in this example class, the plot field is not set during construction, so not set when you call the constructor, and it can only be set to a non-null object by calling this setPlot function. But calling this non-target method as a setup step is not allowed by the strict constraints of EvoSuite's modular testing algorithm, which is limited to generating these prefixes with only calls to the constructor and the target method itself. So as such, the generated tests will never execute get legend item in a non-trivial way with a non-null plot. And this results in poor branch coverage, 1 out of 18 branches. So the resulting test suite fails to execute the majority of the method, and we find that this pattern is quite common and causes EvoSuite's modular testing mode to be ineffective in practice. So this paper provides an exploration of EvoSuite's effectiveness under its modular testing mode. It also proposes a modification to EvoSuite with relaxed prefix constraints, which we call emote, and an evaluation on a subset of the SF100 benchmark. So for this work, we focus on EvoSuite because it typically achieves higher quality test prefixes, and as such is used as a target for reason specification inference literature. So Randoop is another widely used automated test generation tool for Java, and it uses feedback-directed random test generation rather than evolutionary search, but its default mode is also to test an entire program or library, but it also optionally allows for this modular testing functionality. But like EvoSuite, Randoop's modular testing mode imposes strict rules on which program components can be included in test prefixes. So EvoSuite is an evolutionary algorithm for generating test suites. And a general evolutionary algorithm is shown here. The algorithm begins by initializing a population of random solutions. And at each iteration, crossover is applied between two individuals that exhibit high fitness to produce offspring. Those offspring are then mutated with some probability, and they're added to the population, after which the process repeats. So before I introduce our modification to EvoSuite, I'll describe how EvoSuite adapts its general setup to generate test suites for a target class or method. So first we have the initial population. EvoSuite generates the initial population through iterative insertions of random calls which are selected from a pool. This pool is called the test cluster, and it is a set of methods. It contains, when EvoSuite is in full class generation mode, it contains all public methods on the target class and constructors and factory methods for relevant types. So once the initial population is generated, 2 individuals are selected for crossover based on their fitness. And in this crossover stage, these 2 individuals are used to create offspring. Each offspring inherits an initial sequence of statements from one parent and the remaining statements from the other. So because both parents are selected from the population, offspring consist entirely of program segments from this test cluster. So mutation on offspring occurs with some probability. Mutations can involve random deletions, insertions, or modifications. And for insertion and modification operators, these new expressions are also selected from the test cluster. So throughout the algorithm, a key invariant here is that program segments consist entirely of methods from this test cluster. And in this modular testing mode, EvoSuite functions differently by imposing strict rules on which components are included in the test cluster. Under this mode, the test cluster consists only of the target method itself and constructors of the target class type. And these restrictions are imposed in both generation of the initial population and then mutation. So test suites generated in this mode only consist of calls to the constructor of this target type and the specified target method. So our technique, emote effective modular testing with EvoSuite, modifies the EvoSuite modular testing mode by allowing the algorithm access to the class level test cluster during generation and mutation. Our only restriction is that test prefixes must end with calls to the target method. So this allows the algorithm to create test prefixes with calls to non-target setup calls, like setPlot in our motivating example, and is implemented as a fork of EvoSuite. Okay, so allowing freedom in this test cluster also creates challenges. Firstly, it greatly increases the search space. Secondly, a more subtle challenge occurs when the target method is a callee of other class methods. So consider this strip string method from Amazon AWS for Java project. This is from the SF100 benchmark. This method filters characters in the input and retains only those that appear in the parameter allowed set. So it filters characters from the input parameter, including only characters from the string allowed set. And it loops over the input string and checks if each character is in that allowed set string. So an effective modular test of strip string should call with inputs that execute both the true and false branches of line 5. So that is an input containing characters that are in the allowed set, which would cause this if statement to evaluate to true. And another input, potentially the same input, containing characters that are not in the allowed set, causing this if statement to evaluate to false. Okay, so now the surrounding class also includes the method getPrice. This calls strip string with a hard-coded allowed set of digits. And when testing the target method strip string, our modification now allows EvoSuite to select getPrice from the test cluster. So this leads to the generation of test 0 shown here, which achieves 100% branch coverage, but with only a single direct call to the target method. And this direct call only contains input characters in the allowed set, only covering the true branch on line 5. And so this test achieves full coverage, but through an indirect call to the target method through getPrice, which is undesirable in a modular testing scenario. We want to be covering branches through direct invocation of the target method. So we address this through a modification to the fitness function. The fitness function typically calculates branch coverage, but we modify it to only consider branch coverage that originates from a call chain starting with the target method. And this ensures that the reported coverage reflects genuine exercise of the target method under direct invocation. Okay, so we provide an evaluation on a subset of SF100 to investigate if the effect of our modification to EvoSuite. So we ask, given the same search budget, does allowing for selection of non-target methods lead to higher branch coverage? Because it does greatly increase the search space, but unlocks certain branches like we saw in the example. So we set a search budget of 120 seconds for each method, which is consistent with standards in the literature and was also validated empirically on a held out project. And we run each method for a total of 3 trials and report the average statistics. We find that emote achieves an overall branch coverage improvement of 15.15% and covers 304 additional branches across the benchmark. So in total, 162 methods saw coverage improvements under our modification. The highest improvement was in the Jigen project with over 25%, where we noticed that many methods follow this state initialization pattern similar to set plot in the motivating example. And the smallest improvement was on the Riff project, since many of the methods are static and they don't require any setup on a target object. Okay, so we also plot a heat map of coverage achieved using emote on the y-axis and then default EvoSuite on the x-axis in modular testing mode. And so samples above the x equal y line indicate that emote achieved higher coverage than EvoSuite. Here we see that many samples are concentrated in the top left and top right corners, where top left indicates that EvoSuite achieved 0 branch coverage in its modular testing mode, while emote achieved 100%. And the top right indicates that both algorithms achieved full coverage. So most other non-zero components of this grid are above the x equals y line, indicating that emote is effective in increasing branch coverage. Now is an error analysis. So there were 7 methods in our evaluation where EvoSuite without a modification resulted in higher branch coverage, and we explore the reason for this performance degradation. So consider this target method getArtist. Here, the branch on line 10 reads a public field. And this can be directly modified without calling any non-target methods. And so by emote loosening this restriction on methods that we can select, we increase the search space without any advantage. And so for the 7 methods we saw in which emote results in lower performance, they all followed this pattern where branches read from a public field that can be set without calling these setup methods. So in conclusion, we find that effective modular testing often requires setup methods, and evolutionary search tools benefit from flexible prefix generation, even though it increases the search space. And I have the implementation and artifact available on GitHub. Thank you.
Questions?
Great talk, and I was wondering whether you considered a naive baseline of emote where you only, by allowing the non-target methods to appear in the setup stage, but you did not modify the fitness function. Mm-hmm. And I was wondering what is the impact of modifying the fitness function in terms of emote?
So modifying the fitness function actually leads to worse coverage, lower branch coverage. But we do it anyway because this is not a modular test of strip string. A modular test of strip string should call strip string directly. Any coverage that comes from calling getPrice shouldn't be included in an automated unit test of strip string. So our fitness function modification actually decreases branch coverage, but no longer outputs these degenerate tests that aren't actually modular tests of the target method.
Do you have the specific statistics? I'm just curious about the specific impacts on the coverage results.
No, I don't have the specific quantity. I think it varies on the project and target method on like how many other methods would call the target method. But regardless, we don't want a test that looks like this if our target method is strip string.
Okay, thank you very much.
I have one question. Mm-hmm. So I may miss the technical detail, but how did you include those, how did you find those non-target functions that eventually called your target function? Yeah,
so we allow them to select from all public class methods and constructor and factory methods of relevant types. So we essentially allow emote to select from the test cluster that EvoSuite has when it's running in full class mode. And so we don't restrict it at all. We just say you can choose anything that you would choose in normal class method mode, but you must end with a call to the target method.
I see, I see. So do you have the performance for your emote? Like how long does it need to finish the run for the Amazon AWS benchmark?
So these statistics shown here are 120 seconds. So the overhead for collecting the number of public class methods is not significant. Even though the search space drastically increased, we're still achieving higher coverage in the same amount of time.
Cool. Any plan to try your emote on larger programs?
Larger programs.
Or
yes,
real,
I want to try it on defects for J because, like I said, EvoSuite is a target for a lot of recent specification inference techniques, and they're using the prefix from EvoSuite to generate an assertion. And when you're running it under this modular testing mode, if the prefixes are low quality, that might have implications in the specification inference work as well. So
cool.
Yes, future plans to run on defects for J.
Cool. Looking forward to the updated for emote. Any other questions? No? No? Let's thank Elizabeth